So today we'll be talking about lecture 19, which, continuing on with reinforcement learning, we're going to talk about Monte Carlo methods. But first, I just wanted to explain what's going to happen for this lecture. So I've got like 50 minutes to an hour of lecture slides. Then at one point, I'm going to mention a YouTube video that we're going to watch at the very end of the lecture because I don't want it to be in the video. Like, I don't like taking other people's YouTube videos and putting them in my videos. So we'll watch that at the very end, or at least about the first 8 or 9 minutes of it. And it's a 20-minute video. But at the end of the lecture, between the end of the lecture and the watching of the video, I'm going to talk about the optional project for the grad students in the course. So I made a D2L post about it, but I want to go over it. And so that's what we're going to do for today's lecture. But first, lecture 19, talking about Monte Carlo methods. And this is chapter 5 in the reinforcement learning textbook. And I keep extolling the virtues of this textbook, but this is one of my favorite chapters in my favorite textbook. So I would highly recommend reading it before the exam, or maybe even before the assignment. So Monte Carlo methods. Who has heard of Monte Carlo methods before? They're used a lot in statistics and other things. Okay, good. So they're in the context of reinforcement learning. Monte Carlo methods are going to be methods for estimating value functions and discovering optimal policies. So they're going to be one of these methods that we can use to solve reinforcement learning problems. One really cool thing about Monte Carlo methods, which makes them very, very popular and very powerful, is that you do not need to have a complete knowledge of the environment. You don't need to have a model of the environment. In fact, you don't even need to know the rules of the game. All you need to do is be able to identify a state, look at an action that was taken, and then process the reward somehow. So Monte Carlo methods require only experience, meaning that it's a sequence of states, actions, and rewards from either an actual or a simulated environment. And what do I mean by that? An actual experience could be something like a physical robot in a room. When I was doing my PhD at the University of Alberta, they had this robot that was actually a reinforcement learning robot. I can't remember the name of it now, but it was really cool because they controlled it with a Wii remote. And so the robot would like walk around and bang into stuff or like go charge or whatever. And if it did something you liked, you'd hit the plus on the Wii remote to give it a positive reward. And if it did something you didn't like, you'd hit the negative, and then it would do the things you liked more often. It was a cool little robot. So learning from actual experience does not require a model of the environment, right? Like this robot that was going around didn't necessarily know all the physics of the universe or what gravity was or what electricity was, but it knew, hey, the last time I was here, I got a good reward, so I should do that thing. So we don't need to know all the dynamics, the physics, the layout, or even the full state space of the environment to start learning using Monte Carlo methods. So the agent will just take an action, carry it out, get a reward, and then at some point, of course, we're using a computer, so we need to be able to represent that in RAM somehow, and then we can apply these methods to it. When we talk about simulated experience, this might be something like a video game or an actual simulation. Like if you buy one of these expensive robots, typically it will come with software that lets you actually simulate the robot, right? So ideally, if you write this code that performs well in simulation, it should also do the same thing in the real world. And so learning from simulated experience is also powerful because, again, we don't need to know how the model works. We only need that state transition function. And what do I mean by that? Well, the state transition function just says, okay, if I'm in a state and I take an action, what is the state that I end up in? And that's all I need to know. So for example, if you wanted to learn or use reinforcement learning, for example, to play a video game, you don't need to have the source code of that video game. You just need to be able to observe the state, issue an action, and then end up in the resulting action, or in the resulting next state, sorry. If you do have the source code, it'll make that more accurate and more powerful because you could maybe simulate it without the rendering or something like that. But you could, in theory, just look at a video game and what people are doing and reinforcement learn from that. Not only this, but learning in a simulated experience can also then be, you can take that policy and apply it to an actual experience. And a number of years ago, there was a really famous example of this PlayStation hacker named GeoHot. And GeoHot became famous. I think he broke the encryption on the PS2 or something like that. But later on, he was learning how to drive a car by playing Grand Theft Auto. So he was playing GTA 5 or GTA 4 or whatever it was, and basically first-person view in the car. Here is what the driver sees in the game. I'm going to drive around. And now, you know, there are things you do in GTA you probably don't want to do in real life. But he was just trying to follow traffic laws and stuff. And then he took that model, put it into an actual car, and it kind of worked. Like the car was able to drive around this test track. Now you wouldn't want to, you know, put that down in Rollins Cross downtown, of course, but it worked pretty well. So the important thing here is Monte Carlo doesn't need to know any of the rules of anything. It doesn't need to know the state or action space, the probability distributions, whereas in order to use dynamic programming, we do. So we need to know all of those things in order to use dynamic programming, but Monte Carlo is just like, hey, just try it out, right? And it turns out you don't even need to be able to try it out. For example, I could learn, technically, how to play chess just by downloading chess replays from the internet. I don't even need to know how to have played that, right? Like, who here, I don't know, grew up with an older sibling, and as a kid you were like watching them play video games, right? You could learn sort of how to play the game without actually having played it yourself. You're just observing states and what actions this expert took when they were at that state. So that's really cool. So Monte Carlo methods, before I get into the reinforcement learning stuff, the thing they have in common is they all use a technique called sampling. And sampling is just like taking a bunch of examples, right? So who has seen this example before where we use Monte Carlo methods to estimate the value of pi? This is a very famous example for Monte Carlo sampling. If you haven't, it's fine. But what you have over here is you have a square, and that square, let's just say it has side length 1, right? So this is a unit square. Inside that square, you have an inscribed circle, meaning it touches all the sides. So if the side length is 1, that means the radius is half of that, so that's 0.5. So that means that the square's area is 1, and the circle's area, which is pi r squared, is just pi over 4. So what this method does is it's going to generate a bunch of random points for the x and the y between 0 and 1. And wherever that point is, so for example here, this diagram shows 1,000 randomly generated points within this square. And you can see here that some of those points are red. It might be hard to see the actual color. The red ones here mean that they were inside the circle. And so you can tell if it's inside the circle by just using the distance formula, right? Is it 0.5 away from the middle of the square? And so what you do is you keep track of how many of the randomly generated points land inside the circle and how many generated points land outside the circle. And that ratio of how many landed inside the circle to the ratio of how many landed outside the circle should be, if we take enough samples, directly related to the areas of those two things. Because if the areas have this relationship, some ratio, then the number of generated random points that lie within those areas should also be the same ratio if we take enough points. And so if we use this formula, we can see that pi over 4 is approximately equal to the ratio of the number that landed inside the circle to the total number that landed in the square. Okay? And so that means that pi is approximately equal to 4 times the ratio between the number of ones that landed inside the circle to the total number of them. And I just recorded this little simulation here of this website that does this. I forgot to put the URL again of this, but we can see as the number of points increases, the value gets closer and closer to pi. Right? Now, this is a linear thing, so you know, if we do 10 times as much, we may get 10 times as accurate results. And we can see here after maybe a few thousand generations, we get like 3.15 or something like that. So it's not exact, but we are able to get pretty close to this value using a simple method like this. Another reason that, another way that Monte Carlo sampling is used, and now it's not the case that every single Monte Carlo sampling technique involves areas, but it's a really nice visual way of describing it. So over here, what we're doing is using Monte Carlo sampling, just like we did with the circle, to find the area under a curve. And so the area under a curve, if you've done any math, that is the integral. So we can use Monte Carlo sampling to estimate the integral under a curve between two endpoints. And so you're going to generate randomized points in the area. Then, if I generate a point, you can use the function itself, right, because we know this function, to determine whether or not the generated point is above or below the line. And then the area of this under the curve is just going to be the ratio of the points that are below the curve to the total number times the actual area of this rectangle that you're sampling from. So we can use Monte Carlo methods for that, and here's just a couple of illustrations of that, where you can see eventually we kind of do fill up this area. Now you don't have to fill it up, that's just a function of the point size in this graph, but once we have enough samples, then we can pretty accurately estimate these integrals and these functions that may be difficult to compute if we didn't use a method like this. So when it comes to reinforcement learning, we're going to use samples to try and guess the values for reinforcement learning problems. And so it learns based on averaging sample returns. So we're going to take a bunch of samples and then we're going to average those. Now again, I say average here, but we could use any of the update rules that we've talked about, whether it's averaging or fixed step alpha or whatever. And we're going to be discussing first Monte Carlo methods for episodic tasks. So all of these tasks are going to be divided into finite episodes, meaning that they terminate. So this might be a hand of a game of cards or the pole balancing robot example that I showed before. And so value estimate and policy updates are performed only at the end of an episode in this case, right? So we're going to take all the samples until we terminate an episode, and then we're going to go back, look at that whole episode, and then update our values based on that. So we're not doing it every single time we get a reward. We're doing it once an entire episode has finished. So Monte Carlo methods, they sample and average the returns for each state action pair, just like our bandit algorithm that we saw before. And they're essentially going to treat each state as a bandit problem, right? So remember that bandit example we did with the 4 slot machines and we calculated the values? We're essentially going to be doing that update, but at each state. So at each state, you're going to have some number of bandits. And each of these bandit problems are related because of their return after actions depends on neighbors' future actions as well. So this was what we talked about in dynamic programming, how our values are related to our neighboring values. So Monte Carlo prediction meaning trying to guess the value of a state. So our goal is to learn the state values or the action values for given states for a policy that we have. So the value of a state is the expected return, which is the sum of discounted rewards starting from that state. Okay, we've talked about that a bunch already. So the intuitive thing that we're going to do to use the Monte Carlo method for this is to first carry out an episode using the policy that we currently have. And if that's the first time step, we have to have some policy at first. And a typical thing we would do is just say maybe we take each action the first time with like an equiprobable random chance, right? So we need to have some policy at first. Then we record all the states that we visited in the episode. Then we average the return after having visited the states, and we update the value estimate of the state with the average that we just saw. And that's it. So that's what we're going to do, and I'll show the pseudocode for that in the future. And I'll also have another illustrated example like the slot machine one, but we're going to play Blackjack instead. And what happens is this converges to the expected value over time. So if we could do this an infinite number of times, we would get the true average in the end. So just a syntax note, the value, we talked about that last time, that's the expected return. So this is like, we did talk about this, but just as a reminder for the slides going forward. So V pi of S is the expected future return when starting in state S and following the policy. And Q pi of SA, the way that differs from this is that's the expected return when we start at S, but we take a given action before we start using the policy. Okay, so that's what Q pi of SA is. So let's have a look at an example of Blackjack. So who here knows the rules of Blackjack? Okay, maybe just over half. I'm going to go over the rules of blackjack, so if you don't know, don't worry. It's a very simple game. And the reason I use this as an example is because it has randomness, which is cool that we can solve problems with randomness. It's pretty intuitive. It's a very simple card game. So it's easy to illustrate. And also, blackjack is played in episodes, right? So that's really good. You make a bet, you play some cards, and at the end you either win or lose, and we can do it over again. So it breaks really nicely into episodes. Just a quick note before I get into the rules of blackjack itself, the reinforcement learning stuff is that the reward for every action is going to be 0, except the action that stops us playing. So that would mean if we go over 21, that action, then we'll get the reward for that. If we stop getting cards, and then the dealer finishes up their hand, that's when we get a reward. So if we, for example, got 5 cards in a game of blackjack, we would have 4 rewards of 0, and then the final reward, which transitioned us to either the winning, losing, or drawing state, that would be the action for which we get the actual reward. And so a win is going to get a +1, and a loss is going to get a -1, and a draw would get a 0. And this is just assuming that we bet $1 each time, right? Whether or not we put in 1 here or 7 or whatever, all that really matters is that it's symmetrical. So whatever we get for losing or winning, they should be the negative of each other. There's this other rule that's called a blackjack. So in blackjack, the cards have different values. The ones that are most important are all the face cards, so like the jack, queen, king, 10, they're all worth 10, and the ace is worth 11. But if you get a jack and an ace, so if you get a 10 and an 11, and you get 21 on your first 2 cards, you get a little bonus. And so you get a 1.5 reward. So if you bet $100, you would get $150 back in that case, instead of just, yes, so that's a bonus if you get an actual blackjack. So let's have a look at blackjack. I hope this plays. Yeah, okay. So blackjack, just to explain, there are a number of different players playing a blackjack table at the same time. So you could either have 1, 2, 3, 4, 5, however many people can fit at the table. Now, the fact that there are multiple players playing at the same time literally means nothing. You can consider every individual player as an independent player because they're all just playing against the randomness of the dealer. They are not playing against each other. So everyone is evaluated independently. So we're just going to assume that this is a one-player game against the dealer, right? Even though at a casino you might have 5 or 6 different players. The dealer has a fixed policy. So the dealer is not allowed to deviate from the following policy. The dealer, once you have made your decisions, the dealer is going to flip over their card, and then they're going to keep getting cards until they reach 17 or more, and then stop. So for example, if you got to 20, and then the dealer flips over their cards and they have 18, even though they're losing, they are not allowed to get another card, right? So the dealer is just, for example, it's just the randomness of the environment. So the dealer is not considered a player here. Blackjack is not a multiplayer game. You're not playing against another player. The dealer is just the environment with a fixed policy. So I just want to make sure that you're aware of that. This isn't like chess where the dealer makes a move and then you make a move and you go back and forth. So here's what happens. Every player at the table is going to be dealt 2 cards. The order in which the cards are dealt, typically you get 1 card for each player, then 1 card for the dealer, and then 1 other card for the player. But you can assume the deck is randomized, and so it doesn't really matter what order the cards come out in. All that really matters is that each of you get 2 cards, and the dealer gets 2 cards, but one of the cards is secret. And that's what creates the drama of blackjack. So right here, the dealer has an 8, but you don't know if the card underneath the dealer is a 10, meaning they have 18, or if it's a 3, meaning they have 11, or what, right? So what you're doing is you're trying to play this overall average best strategy. You can't know exactly what the dealer has. Okay, so that's how it looks in the casino, but just remember that each of these hands is being played independently. So whatever is over here has nothing to do with whatever is over here, okay? So here's what happens. So we're going to put the dealer cards on top and we're going to put the player cards on bottom. The cards are shuffled and then they're dealt to the dealer and the player. Again, the order in which they are dealt doesn't matter. Just as a side note, in an actual casino, instead of just using one deck of 52 cards, they typically put like 10 or more decks into this giant automatic shuffling machine that they call the shoe. And the reason for that is because if you only played with a deck of 52 cards, it would be really easy for the players to memorize exactly what cards are left in the deck. And if you're capable of doing that, you can actually change your strategy a little bit and actually win at blackjack. So they want to simulate an infinite deck of cards so that you can't have any extra bonus information. So the cards are shuffled. In this example, I'm giving the dealer their cards first, but again, you saw how that it doesn't really matter what order they come in. And so the dealer is going to have one card face up, meaning 4, and one card face down. And so you don't know what that one is yet. And then the player, you're going to get 2 cards as well. So here, this is the starting state. So this is the starting state of the episode after the first deal has been done. And so we're going to say that S sub 0 is the player has 7 and the dealer is showing a 4. Now, you might say, well, we don't really know what the state is, right? Because we don't know what the dealer's card is. But it doesn't matter, because every time the dealer's showing 4, you kind of, the same policy applies. You've got to do the average best thing because you can't know. So even though you don't know exactly the full state of the game, this is the state because this is all the information that you have to make decisions with, right? It's like if you had a self-driving car, the state would be what you could see, but maybe you can't see what's in front of you, or like what's in front of the car in front of you, or something like that. So we're just going to represent the state as a 2D array with the counts as the indices into those. It's just an easy way, right? So this is state 0, the initial state. And my actions in blackjack, I'm going to play a simplified version of blackjack. Because in the actual game of blackjack, there are other rules where, like, for example, if you get 2 of the same card, you can split and play 2 simultaneous hands. Or you can double down, meaning I get 1 more card and the bet goes up. There's all sorts of different things, but this is a simplified game of blackjack where all we can do is hit. Now, we're not going to like punch the dealer, right? Hitting just means give me 1 more card. This is just the slang for blackjack. So hit means give me 1 more card, and stand means, they also call it stick, which is I don't want any more cards. And if you take the action stand or stick, then you can't get any more cards for that hand, and you're at the whim of whatever happens with the dealer's card. So the last action we will take is typically a stand, unless in blackjack, if we get another card that puts us over 21, we automatically lose. That goes right into a losing state, no matter what happens to the dealer. So even if the dealer busts, if you bust, you lose. That's one of the things that makes it unfair for you, is that if you both lose, no, you actually lose, not the casino, of course. So this would be really boring if I didn't hit. So I'm going to make my initial policy just to hit until I get to 20 or something like that, right? So let's say that my policy says if I have 7 and the dealer has a 4, then I'm going to hit. And hit means I'm going to get another card. And in this case, the state has been updated, right? So the state is updated, I've been given a 2, and now my sum is 9. So that means that S1, which is the second state after the first action, is 9-4. So we went from 7-4 to 9-4 because now my sum is 9, okay? And the first reward that we got was 0. Why is the reward 0? Because the episode hasn't finished yet, and in blackjack, we don't know if we've won or lost until the very last action, okay? So that's state number 1, and now this is how we're currently dealing with the game. So if I have a 9 and the dealer's showing a 4, what should I do? Anyone in the audience? Hit? Yeah. Typically, if you're at no risk of busting, you should hit, right? So we're going to hit again, and this is now A1, because this is the action that we took at state 1. And, okay, I got a 5. So my state is now updated so that I have 14, which was 9 plus the 5. The dealer still just has the 4, and R2 is 0, because this was not the final action yet. I'm feeling a little bit spicy, so I'm going to keep hitting at 15. And look, oh, I got a 6. Oh, sorry, I had 14. So this is, now the sum is 20, and so state 3 is 20 and 4. My reward is still 0 because the hand hasn't ended yet, right? And so, okay, I have 20. If I get anything above 21, I'm going to bust, so I should absolutely not get another card here, right? The only card I could get and not go over would be an ace, because an ace lets it be 11 or 1, depending on that. So I'm going to choose to stand. And when I choose to stand, you can picture this as the state moving instantly to either win, lose, or draw, right? Now, because blackjack in a casino is like a physical game that a human has to actually implement this, then the dealer's going to keep taking, well, they're going to flip over their card and keep taking cards until they get to 17 or more. So let's see what happens in this case. So the dealer, it turned out, had a 5 underneath. So they had a total of 9, which is under 17. Then they hit, so now their total is 12. And so they had to hit again, and they got a king which is worth 10. So they went to 22, and so the dealer busted, right? This never happens to me when I play. They would have just flipped over the king right away or whatever, but the dealer busted. And so that means we have transitioned to a winning state, okay? So standing instantly transitioned me to a winning state. Hopefully you can see how the dealer is just this function of the environment. It's like if they had rolled a dice, for example. But maybe this had happened where instead of getting the king to go to 22 and busting, they got a 9 and they got 21 and win, right? So this just shows you how in the same state with the same action, I ended up in a different state, right? In one deal of the cards, I said stand at 20 and the dealer lost, so I went to a winning state. In the other deal of the cards, I chose stand at 20 and the dealer got a 9, and so I went to a losing state, right? So there is a probability in blackjack of going to a winning state or a losing state, and we haven't calculated those probabilities, so we don't know those things yet. But also maybe the dealer got an 8, in which case we would have drawn, right? So there are 3 possible things that can happen after I take the action of stand. So once the dealer gets all their cards, it's either win, lose, or draw, and it would be +1, -1, or 0 if it was win, lose, or draw. So let's just have a look at this more mathematically and less graphically. So the dealer got a 4. The player got dealt 4-3 at the beginning. I'm just replaying this hand again, but sort of in text. Dealer showing a 4. So this was state 0, 7-4. My action was hit. I got a 2. My reward was 0. Next, because I got a 2, state 7-4 went to state 9-4. My action was hit. I got a 5. The reward was 0. 9 plus 5 is 14. So it was the state 2 was 14-4. My action was hit. I got a 6. The reward was still 0. Then the state was 24. The action was stand, and the reward was 1. So the reward was 1 here because that was the hand that I won the game. But if that was the hand where I lost the game, so state 4 would be the winning state. And in the winning state, I get a reward of 1. If that was the case where I had lost, then the reward would be -1, and S4 would be lose. Okay? So hopefully you can see how this is working now. We just take samples and we write it down. Now, let's look at the whole episode in a little bit easier format. So the state sequence was state 7-4, 9-4, 14-4, 24, and win. So that was the state sequence that we went through. The action sequence was hit, 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 stand. Or, if you're doing this with integers, it might be 1, 1, 1, 0, or whatever my actions were. Did you have a question? Can I just finish this slide first, and I'll get to your question? So the reward sequence was 0, 0, 0, 1. But the important thing here is that the future return sum was 1 for everything. Why? Because if I calculate the return, which is the sum of future rewards, from the start to the end, the sum of 0, 0, 0, and 1 is 1. The sum of, for the second one, 0, 0, and 1 is 1. The sum of 0 and 1 is 1. So this means that when I go to update my values, my return, which is the thing that I actually use to calculate the value that I'm going to update for the episode, the value for all this, or the return for all of these states was 1, because it was a winning state, right? I wouldn't want to update 7-4 with the reward of 0, because then I wouldn't learn anything about what happened, right? Because it didn't draw. It actually went to a winning state. And so that's why the future return sum is so important. Your question? Sorry? The 4 here? That's the dealer's card. Yeah, so I'm representing the state by my sum and the dealer's card. So back here, yeah, so this is the state down here, 14-4. It's because my sum is 14 and the dealer's card was a 4. Was that your question? Okay, perfect. Yeah.
I just had 2 questions. One was when we are showing the states, the last state we show as win.
Yeah.
Why don't we have the state which shows the state after the dealer's policy, which would be like 2021?
It literally doesn't matter.
Okay.
Right? All that matters is that I win, lost, or draw. Because if I have, let's say I had 17. It doesn't matter if the dealer has 18, 19, 20, 21. It's just win, right? Because the MDP says, what is the reward from me taking an action at a state that brings me to a winning state, right? And so you could implement it that way, but it's just more work. Yeah.
And the last one I just wanted to ask, is the future return sum calculated only after the entire scenario has finished, or
after the episode?
Okay.
Yeah.
Because I wanted to ask then how would the 1.5 reward be accounted for? But
well, then our return, our reward at the final state would have been 1.5.
So each step would have
exactly, right? So this is why, because while I'm playing the game, I'm getting 0 rewards because I don't know if the thing I'm doing is good or bad yet, right? Now, let's say, I'm at 20 and the dealer's showing a 4. I'd say 80% of the time, you're going to win that hand, right? So if you played this 1,000,000 times, 800,000 of those, your reward, your return for all those states would be 1. And 20% of the time, they would be -1, right? So the average of all of those, you would probably see your value of that state being close to 0.8, which would be very high in terms of blackjack. You're not always going to win, but you're usually going to win. So let's have a look here. Okay, that slide was made a little bit weird. So if we want to update the QSA value estimates, what we're going to do is we're going to use the return sum, right? We're using the returns here to update it in Monte Carlo, where we're talking about an episode. So once the episode is finished, we look at an action. What value do we want to use to do the update step? It's the sum of everything that happened on that action to the end of the episode. So in this case, all of our updates would be using 1, that we want to pull our estimate closer to 1, because this is a winning strategy. If this was a losing strategy, then that would be a -1. If it was a draw, then it would be a 0. If it was v pi of s, typically when we're doing reinforcement learning, we don't actually store v pi. We're going to be storing q, right? Because we want to know the values of actions rather than the values of states. Okay, so here's the algorithm that we would use. The first algorithm we're going to look at is called every visit MC prediction. Every visit means that after the episode has been terminated, we go back and look at all the different states and action pairs, so all the state action pairs that we did in that episode. For every single one of those, we are going to do an update of the value. Okay? There's another algorithm called first visit Monte Carlo, in which if a state action pair appeared multiple times, we would only update the value for the first time rather than every time. So the difference between every visit and first visit is just how often you do the updates. So let's have a look at that algorithm. It's pretty simple. So QSA is going to be where we store our state action pair values. So that's just some array or whatever data structure we use. In this case, what I'm going to do is I'm going to use that very first method where I actually keep track of every single return I ever got. Okay, so I'm going to keep track of all the returns and then take the average of those rather than the incremental update. So while true, this means for any amount of episodes that we want to do. So, again, this is keep doing it until an hour is up or, however much compute you have. So we're going to generate an episode with our policy. So we have some initial policy, and then that policy is going to generate an episode, which is the initial state, the initial action, the reward, state, action, reward, state, action, reward, all the way up until the end. So that's the episode. I'm leaving this line blank intentionally. We'll see why that is in a bit. So then we're going to loop over all the time steps in the episode, because at each time step in the episode, I have a state, I have an action, and I have a reward. So I'm going to calculate the return of everything which is the sum from this time step until the end of the episode. Okay, so that's how I got all those ones. So I'm going to say, what did the episode give me from here on when I did this, right? Then I'm going to append that return to the returns that I saw from this state and this action. So for every state action pair, so for example, if I had 14 and a 4 like we had, if I played 1,000,000 hands and I saw the state 14-4, I don't know, 10,000 times, then I would have 10,000 values here, so I could take the average of all of those. Then I'm just going to set Q of SA equal to the average of those returns. That's it. And then, so that's the algorithm. It's pretty simple. We do an episode, then for every state action pair in the episode, I update its value based on the average of the returns that I've seen ever from that episode, right? So if I had, let's say, state 14-4 again, if I did that, if I saw that state 1,000,000 times and I won 80% of them, then my value here would be close to 0.8. If I lost 80% of them, it should be negative 0.8, right? And so what that should tell me in the end is that for this state, let's say I have two different actions, hit or stick. If my action of hit has a value of 0.8, and my action of stand has a value of 0.4, which action should I do? I should do the one that has the value of 0.8, right? So this is the reinforcement learning part where I record the values of things. So we want to estimate either the value of the state, or more than likely, the value of the action at that state, given a set of episodes obtained by following some policy. Each occurrence of a state S in an episode is called a visit to S, and each episode or each state may be visited multiple times in an episode. Now it turns out in Blackjack, because your score keeps going up, like by definition you can't get a negative card, then it's impossible to visit the same state twice in an episode of Blackjack. But if we're thinking of pathfinding, for example, maybe I went to the left and then I went to the right. So it's very possible in a lot of environments for you to visit the same state more than once, or state action pair more than once in an episode. If that's the case, where you have an example of where states can be visited multiple times, then there's another algorithm called first visit Monte Carlo, which estimates it as the average of returns following the first episode, or the first visit. And every visit Monte Carlo methods have different theoretical properties than first visit, and I'm not going to get into all of those details because they don't matter, but I just have a few comments. So every visit MC may update a state value for a single state multiple times if it's visited more than once during an episode. So think about this. If I have an episode in which a state was visited multiple times, if I do every visit MC, let's say the reward was a win, for example, right? Then I see the state once, I'm going to update its value to be closer to a win. Then I see that same state later on in the same episode, and I update it again to be closer to a win? Do I actually want to have updated it twice when really I only got one reward from that episode? I really only have one example of it winning. And so this is why the theoretical properties and stuff of Monte Carlo methods, of first visit MC works out a little bit better. So it's probably the case that you want to only update the state action pair value the first time you see it in an episode rather than every time you see it in an episode.
Sorry.
Yeah, just let me finish this slide. Yeah, so try updating the states on first visit only, and let me just do one more slide. So this was every visit Monte Carlo, and this is first visit Monte Carlo. All you have to do, if you see, all I'm doing is, I'm not going to call it a closed list, but it's kind of like a closed list, right? Where every single episode, I just keep track of which states have been visited. And then down here, I say, if it has been visited, then continue. So I wouldn't be updating anything for that step. And then after this, after I've updated it, then I add it to the visited. So the first visit Monte Carlo is the same algorithm as every visit Monte Carlo. I'm just saying, okay, if I've already seen this state, this episode, then don't update the value for that. So that's first visit and every visit Monte Carlo. Yep.
This is probably a stupid question, but why the first instance? Why not the last instance? Shouldn't the last instance have more information?
So technically the first instance has more information because more things happened after it.
Okay.
Right? So you want to take the thing with the deepest amount of knowledge to be the way that you update things, right? So that's the logic that people are using.
Sorry, because
Yeah.
we are estimating the value based on the following steps, not on the previous steps. That's why the first instance has more information than the...
Well, for example, in the pathfinding case, let's just say that I moved left and right a bunch of times, right? And then at some point I stop doing that. And then maybe I have 3 more steps to go, right? The first visit to that state, well, there's 12 actions left. But the last visit, there's only 3. So I probably get more information about that. You guys are just being a bit loud while you're talking. Yeah, did you have a question? Yep. Yep. Yeah, so the return array, let's look at this code. So it says, for each time step, calculate the return following this time step, right? So if all of my actions are 0, 0, 0, 0, 0 until the last thing, which is a 1, then what are all of my sums following this time step going to be? All of them are some number of zeros and then a 1. So all the sums are 1, right? Now, it may be the case that you don't have a bunch of zeros and a 1. So for example, let's just say that I had, okay, let me just see if I can draw this because I don't want to exit PowerPoint. Let's say I got 1, 1, 1, 1 as my rewards from the episode. Then the sum following this one would be what? What's that? Well, how many are there? 4, right? So that would be 4. The sum following this one, 3, 2, 1. So that would be the array if I got a 1 at every reward. But because I got a 0 at every reward, that's a J, sorry, I'm real bad at this. Here we go, let's just draw a stick figure. So if I got zeros until I got a 1, then the sum following this one is 1, the sum following this one is 1, and the sum following this one is 1. So it's a good question. It's not obvious at first, right? But what we're trying to do is we update things based on the entire return of the episode following this state itself, right? Now, there's a bunch of states of Blackjack. There are thousands of them, or maybe I'd say hundreds of them. There are hundreds of states of Blackjack, and we only visited 5 of them during this thing, so only 5 of the states are going to get updated based on this return. Okay, so we'll go to where we were. I mentioned this a bit last time. In order to use something like dynamic programming for Blackjack, even though we know the rules of Blackjack, and we could very easily program the game of Blackjack, it's very difficult to use dynamic programming when with a game like Blackjack. Because for dynamic programming, I would need to know what's the probability that I win from this state. Like, what's the probability that I go from this state to the losing state, or this state to the winning state? And if I had all of those probabilities, I would have already solved Blackjack. So I would have to do a ton of work just to be able to use dynamic programming, and it turns out in this case, the amount of work would be solving the game itself. So in games with randomness, especially, it's often hard to use dynamic programming. So just the example, what's the probability from this state that I would lose if I had this? Well, if I had the probability of winning using stick versus using hit, then I would just take the one that had the highest probability. So I've already solved the game, so it's difficult. And they must be known when I'm using dynamic programming. Monte Carlo doesn't care. It doesn't need to know about randomness. It doesn't need to know about rules or anything. It just takes the average of what you've done. Okay, so Monte Carlo estimation of action values. Now that we have state values, how do we form a policy based on those? So without a model, we can't tell which actions led to other states just using samples. So we must calculate the value of doing an action at a particular state in order to know which action is best. So this is saying that when we do this, the reason we use QSA to store action values at a state instead of just the value of a state is because we need to know which action took this value, right? We don't always know. In dynamic programming, yes, in that simple example I gave before in the previous class, I could look up, down, left, and right. But in Blackjack, there is no up, down, left, and right. I've got to know probability distributions and all sorts of weird stuff. So Q pi of SA, that is the expected return when starting in state S, taking action A, and then following policy pi. So that is the thing that we're computing. And then once we have that value, we can look at the values of doing all the actions and take the one that's best. All right, exploration. For many problems, the number of states and actions is pretty large. And if we follow this given policy, we'll keep doing the same thing over and over and over. And we have to be careful to explore, to choose actions that have not been done before, because let's say, for example, I'm learning to play basketball by watching the NBA, right? So what have I learned? Be 7 feet tall and just dunk on people. That's the strategy I should implement when I go to the gym, right? Now I get to the gym and I very quickly realize I am not able to dunk on people and I don't know what to do because I've never watched a bunch of fools play basketball of which I am one, right? So we have to make sure that when we're doing these methods and we generate our episodes, that there's a lot of variance in the episodes. We don't just take an expert blackjack player. We don't just take an expert chess player. And this has happened, literally, it happened to AlphaGo, to DeepMind's, like it's happened to chess programs in the past, where they trained this system on professional players, and then they're playing against a human that does something crazy, leading them to this weird state they've never seen before, for which they don't have a good action value for. And so they just think, oh, I've never been here before, maybe my value estimate is still 0, and so just do a random action. I don't know what to do here, right? So the good thing about machine learning in general, as well as reinforcement learning and Monte Carlo methods, is that they don't need to know anything, right? I can just make observations, see what effects these actions have and what rewards and returns they lead to, and I can learn based on that. But the downside of these algorithms, unlike something like search, which does things exhaustively, is that if I'm ever in a real scenario and I'm in a state that I've never been before, I have no idea what to do at this state. Now, this problem has been alleviated a little bit in more modern cases of like neural networks, right? Because neural networks are very good function approximators. So if we're doing this in a table, in an array, and I go to look up a value for a state that I've never been in before, that's just going to be like a 0, right? But maybe in a neural network, because they're good function approximators, even if I pass in an input I've never seen before, maybe it will end up being something like the value of its neighbors or the median or whatever. So neural nets have helped this a little bit. But the key thing here is that in order to be able to do a good thing in a situation, you have to have trained in that situation, which is the downfall of machine learning. And it's why all these companies are so hungry for data, because the data are the visits to these states. That's the analogy here. Okay, so what this means is that while I'm taking actions or while I'm playing the game, make sure that sometimes I take an action that isn't very good. I've got to learn about the value of actions that aren't good too. I've got to lose my queen sometimes in order to learn that losing the queen is a bad thing. So things like epsilon greedy action selection help us to explore and to do that. So Monte Carlo control, now that we have the values for state action pairs, how do we use those to update the policy? Well, we just remember the bandit algorithm selection. It's no different. So we've seen how to estimate values given a fixed policy. How do we update the policy to perform better over time? Well, hopefully we learn the values of QSA and we get more accurate estimations over time, and that will guide our policy over time as well. So this is called policy iteration. And so we went over this a little bit at the very end of the last lecture, but once we have a value estimate, that is new information, right? And we use that new information to update our policy, and then we're going to use that new policy to update our information, and then we're going to use that new information to update our policy. And this is called policy iteration, or generalized policy iteration, or GPI. So in GPI, we're going to maintain two things. We're going to maintain our value function estimates, so that's our Q array that we're looking at. And we're also going to maintain our current policy estimates, so what we should do at each state. And so the value function is going to be repeatedly updated to more closely resemble the true value function. And what that means is, as we get more and more samples, our Q estimates are going to approach the actual averages. And then the policy is going to be repeated to improve based on those values. So there's two main steps here. Policy evaluation and policy, I think this should be policy improvement, because policy iteration is the whole thing. So policy evaluation, policy improvement. If I ask the two steps on an exam of what GPI is, policy evaluation, if you say iteration or improvement, that's fine, because I think I go interchangeably back. So policy evaluation means take the policy, carry out some number of samples in episodes, and then use the returns that you got from those episodes to update the value to more closely resemble the true average. And then once you have that value updated, now you go look at the values of all the actions and you update the policy to be greedy with respect to the current value function. So these processes alternate. One completes before the other. So you'll do an evaluation, iteration, evaluation, iteration. So GPI refers to the general idea of letting policy evaluation and improvement interact to improve a policy over time. And almost all reinforcement learning methods resemble GPI in some form. Now, with more modern, like deep reinforcement learning methods, and you have a neural network, sometimes what they do is they can directly encode the policy rather than having to have values. But for GPI in general, we do keep track of the values, and then we look at the action values in order to decide what to do. Now, just a quick note is that even though I say these two things alternate back and forth, it doesn't always mean that I always have to do just one of those things, right? So for example, there are some things like batch methods when you're talking about Monte Carlo, where I might play 1,000 hands of blackjack, and then update all my values for those 1,000 hands, and then do one iteration of policy improvement, right? So it doesn't mean I only have to do one of them, but I would do some amount of evaluation and then a step of iteration. I like these illustrations that the book has, this one especially. So over time, two things are occurring. the values are approaching the true average values, and the policy is going to approach the optimal policy. So what we see over here is that we're going to start at some v and pi. Sorry, I know this is a bit small. So we have some initial policy and some initial value estimates. So maybe this policy is random and maybe the value estimates are all 0, for example. And then what we do is we do one step of evaluation. And for every step of evaluation we do, we are updating the values to more closely resemble the true values of the policy. Then after we do that, we update the policy to be greedy with respect to the values that we have. Then we go another evaluation, improvement, evaluation, improvement, evaluation, improvement. And ideally, this is converging so that once our estimates get close to the true value, then if I knew the exact actual averages, I can just take greedy things. And if I'm taking greedy actions with respect to the true averages that we've just found out, then my policy is going to be the optimal policy. Okay, hopefully. Over here, this is just another view of this. We take our policy, we evaluate it, right? So our value estimates go to be more closely related to the true value of that policy. And then we take that and we update the policy to be greedy. So there's lots of diagrams in the book, which is why I highly recommend reading that. So policy iteration, how do we apply policy iteration with MC methods? Again, we've already covered policy evaluation, so we update the value estimates after an episode has been generated. And then policy improvement, yeah, here I call it improvement, update the policy based on the new estimates. And so again, another thing from the book, we have our initial policy, we evaluate. This leads us to initial Q values for our policy. Then we improve and we update our policy. Or sorry, this is the Q values, the estimates. Then we improve our policy based on that, and we get a new policy, evaluate, new values, improve, new policy, evaluate, new values, improve, new policy. Okay. And then policy is updated exactly the same as with our bandit method, which is just, hey, we look at the value of the actions and we take the action that has the highest value. So here it is in a nutshell. In general, this is Monte Carlo policy iteration. We have some initial values for our QSA value estimation, and we have some initially probably equiprobable policy for taking actions at each state. And then while true, so while true here just means for some number of episodes, we're going to generate an episode based on the policy. We're going to update our value estimates based on the episode returns. We just saw that algorithm. And then the thing that was left out of that algorithm is the last step, where we update the policy to choose the actions with the max values from our Q values. Okay, so Q estimates the true values and P estimates the true policy. And if you do this for Blackjack, you end up getting a table like this. And then you can take this table to the casino, right? Now, no, if you have, actually, I don't even think they care anymore if you bring in a policy. I don't know. But maybe don't test it out. Maybe ask before you pull out your phone with the tutorial on it, right? Because there's two, I guess if you're a casino owner, you kind of want someone playing who needs to have a policy in front of them to like, oh yeah, you don't know the rules? Come play all you want, right? So yeah, but this is what you'll end up with if you play this. Now, this can be a little bit deceptive as well. The reason it may be deceptive is because this shows the policy only. It doesn't show the values. And it may be the case for some of these bordering states, like for example, this is probably not the case, but let's just take an example of this is a stick right here, or a stand. The value of standing here may be 0.49, and the value of hitting here may be 0.48. They may be actually really close, but all you're seeing here is the best one, right? So I've never seen this before, and when I get to the project part, maybe one of you can do this. I would like to see kind of a little slider there, right? Instead of just saying S, maybe if the two values are similar, you draw a line down the middle, right? And you'd say, okay, sticking is marginally better, and you could see that. All right. MC with exploring starts. Exploring starts are cool. So many problems have large state and action spaces, and in practice, many state action pairs will not be visited often. So when generating episodes, it is important to vary the starting state to ensure all states get sampled. This process is called ES, or exploring starts. Now, Blackjack, because it's randomly being dealt out, has exploring starts built in. But picture we have a pathfinding environment, like our assignment is going to be. You wouldn't want to start every episode on one tile. You'd want to start one over here, and one over here, and one over here, and one over here, right? Teleport around for your start so that you can learn more about the entire map. So it's important to explore not only when you select actions, but when you actually dictate the starting state as well. So Monte Carlo ES, all returns for state action pairs are just simply accumulated and averaged. So the algorithm doesn't change, it's just the starting state. And a really cool property of Monte Carlo ES is that Monte Carlo ES cannot converge to a suboptimal policy. Now, that doesn't guarantee that it's going to converge, but if you see that it does converge, you know you have the optimal policy. And convergence there would mean any number of things, but it means that essentially you keep doing it and things are no longer changing. Like your policy is no longer changing. Like for 1,000,000 time steps, it keeps telling me to do the same thing. Okay, we're probably converged. So the cool thing is, if at some point your policy that it is currently at is bad, then you'll be taking bad actions. Those bad actions will update the values of those actions with poor returns. And then the next time you go to update your policy, you'll look at those poor values and you'll say, I don't want to do that, and then you'll do the other thing. So it can't converge to a bad policy, right? Because if it did, it would see that it was bad and it would change the actions. So it's sort of this like self-healing thing. Yeah, it might go down a weird path, but it will eventually get out of that. It can't converge down there. So convergence to the optimal policy is intuitively inevitable, as changes in the action value function decrease over time, but as of the writing of this slide, that fact has not been proven. But anyway, it's really good. So in practice, Monte Carlo with ES converges kind of slowly because it's hard to visit a bunch of different states. So if all we did was use exploring starts and not randomize our actions, then we would still visit only a few states. So we still also want to explore while generating the episodes. So like we talked about epsilon greedy, maybe 10% of my actions should always be random. So I'm starting in random places, sometimes I'm taking random actions, and so that's good. By including randomized actions, more states get visited, more actions get sampled, and we learn more quickly. And it turns out that in some problems, you actually just want to do random things. You can actually learn from just pure randomness. Because when I saw that thing happen, it was good. When I saw the other thing happen, it was bad. So Monte Carlo uses sampling to generate episodes with state action reward pairs. Value function estimate is updated at the end of each episode via rewards that were obtained. The policy is updated to reflect the new estimates. New episodes are generated with the new policy, and this cycle, GPI, just keeps happening over and over. And varying the starting states with ES and action selection can help visit more states and converge to an optimal policy. So there's a video here. The content of that video can and probably will be on the exam. I'm going to ask a question about this video. Here are some other exam questions, but I'm kind of running out of time, so I'm not going to read those. I'm just going to leave you there for that. Okay, but first, discard. All right. First, I wanted to very quickly go over this for the 6980 students. This is the post that I made, so 3,200 students, you don't really have to. What's going on here? Course home. Okay, so this is for 6980 students only. This course will have an optional bonus project that you can do to increase the grade in your course. The reason I only do this for the grad students is because there's way too many undergrads, and I don't want to burden you with an optional project, and I don't want to mark them, honestly. But grad students every year, because grad students have a 65 to pass the course instead of a 50, so the grad students come to me, oh, I got a 59, I just need 5% more, please, I'm gonna have to go back to my home country and join the military. Like, you'd be, like, that has literally happened to me multiple times, where if I don't pass this course, I have to go join the military. Anyway, this is your chance to get up to 10% bonus marks in the course. But you can't use that 10% to go above a 95. That's, you have to earn 100 in this course. You can't just get it with the project. This project is worth up to 10% bonus for the year, which will be added to whatever grade you get at the end of the course without the project included. It can't make you go over 95. This is not, yeah, blah, blah, blah. Okay. The project is due April 19th, which is the latest I can possibly have it due and still get it marked in time. And in fact, I'm probably not even going to be finished marking the friggin' exams by the time this is due, but I'm trying to give you as much time as possible. That is a month from today, okay? You do not need to inform me of your intent to do the project. What will happen is, on April 19th, at the due date, I'm going to check the folder, and whatever is there, I'm going to mark. And if you're 1 minute late, I'm not going to mark it. Okay? You've got a month. I'm not listening to any, I don't have time. These are optional projects. It's either there or it isn't at 11:59. There will be absolutely no late submissions. The project must be done solo with no partner. You cannot get your grade increased because your partner is really good. The overall project will be probably as much coding as assignment 2, plus the writing of an analysis document. So you're going to have to give me a little PDF showing me some stuff. If this seems like a lot of work, keep in mind it's optional for those people who would have come crying to me to pass the course, okay? So you don't have to do this. But if you want a better grade, you can do this. Blah, blah, blah. If I determine that you have used any AI tools to write any of the code, I'm just going to fail you, okay? Because last year, I had 7 people do the final project, and 5 of them were 100% AI slop. I didn't automatically fail those people because I didn't have this policy in place. I wish I had, because that was pretty insulting to give people like this second last chance. Even the report, all AI slop, just like a LinkedIn post. It was garbage. And what happened? 2 of those people had a 60, and 2 of those people, I didn't help them get to a 65, which I would have gladly done if they hadn't used AI. Now, this isn't me just like oh, I sort of suspect it. Don't be afraid to do the project because I might suspect you of using AI. This will be, you know, a pretty intense process of me being 100% sure that you used AI. Okay, project details can be found here. I'm not going to go over them all because this is here and people can message me on Discord or whatever. I don't have a lot of time left in this. Go away. But essentially, you'll be taking assignment 5, which is on Q Learning and SARSA, and you will be taking the pathfinding assignment that we're doing for assignment 5, which we haven't done yet, and you'll be changing it to make it Blackjack. So the optional project is to solve Blackjack and to write a custom UI that is like assignment 5, but instead of each square being a state in that environment, it is now, you should produce something that looks like this. So this should be like the output of your final Blackjack project, okay? All the details are there. There's a big report you have to write as well to say sort of what you learned, which one was better, etc. Here's the description. I'm not going to go into all that because you're all capable of reading that. But if at any point you have any questions about the final project, just let me know. Okay. So that's it for the grad students. There is an optional project. Now, technically we have 6 minutes left. I'm probably going to play 8 minutes of this video because I think it's really cool. It's one of the coolest videos I've seen. And keep in mind when watching this video, the matchboxes, they'll explain the matchboxes. They're not storing values. It's storing the policy directly, and they're directly updating the policy. And that is a really cool thing. So instead of storing values, they store the policy distribution itself. and how that works out ends up being really cool. So for anyone watching the video, it's going to stop now, and then go watch the Menace video, because a question will be on the final exam about it.